Okay, so here's a problem that you probably won't have seen before. We're going to start with 3 piles of coins, and they're all empty to begin with. So let's put 4 coins in one of these piles. So you can really think of this as a game. The idea of the game is to move the coins around in a certain way. So every time you can move 1 coin however you like. There's only one restriction, and that is that whenever you move a coin, it has to end up in a pile which has less coins in it totally than where it started from. So if you like, you can think of these coins as kind of self-hating. So the coins hate other coins. So the coins want to move in such a way that they minimize the number of coins in their pile. But you don't need to think about it in such a complicated way. Basically, any coin move is okay, just so long as after that coin's moved, there's less coins in the pile where the coin is. So for example, if you've got this coin here, it's in a pile of 4 coins. So it could move over here, and now it's happier, because it used to be in a pile of 4 coins, now it's just in a pile of 1 coin. This coin here, again, can move over here, because it's in a pile of 3 coins. If it moves over here, it's in a pile of 1 coin, so that's a legal move. However, we cannot move this coin here to here, because that doesn't decrease the kind of congestion of the coin. It doesn't decrease the number of coins in its pile, because it used to be in a 2 coin pile. If it moves over here, it's still in a 2 coin pile, so that doesn't help it in its quest to avoid coins, so it's not a legal move. So that's the game. We start with so many piles and so many coins, and we're allowed to move around in this fashion. And so there are different puzzles related to this thing. And I don't think you'll have seen them before, because, well, a fair amount of this came from my own research, so unless someone else has done the same thing and I don't know about it, you probably won't have seen all this before. So the first problem is, what's the so hopefully you can see that if you keep playing this game, you're eventually going to run into a kind of position where you can't move anymore. So let's call that a fixed point. Okay, so the first question is, what's the fastest way to get to a fixed point? Well, if we just move a coin from here to here, that's 1 move, and then we go to here, that's 2 moves, and now you see we can't do any more moves. So in this case here, we can get to a fixed point within 2 moves. Okay, so now let's look at something a bit more interesting. Let's look at this puzzle with 5 coins now. So again, I ask, what's the fastest way to get to a fixed point? Can you think of a special way to move these coins so that we're going to end up at a fixed point as fast as possible? And what do the fixed points look like in general if we have a general number of coins and a general number of piles? You can think about these kind of things. Anyway, if you want to think about it, what's the smallest number of moves to get to a fixed point? Pause the video, have a think. Otherwise, I'll show you the answer. So here it is. We can get there in 3 moves, like this. 2, 3. And you can see that no coins can move and decrease their kind of number of coins in their pile. So this is a fixed point. Okay, so the first proper puzzle then is, so in this case we have 5 coins and 3 piles. My question is, if we have 10 coins and 3 piles, what's the smallest number of moves that you have to do to get to a fixed point? And remember, a move is where you move a coin in such a way that you decrease the number of coins in that pile. So I don't think this is a terribly difficult problem, but have a go at it. Okay, so now let's have a look at something a bit more interesting. what is the largest number of moves we can do in this game without getting to a fixed point? So let's have a look at this situation again, where we start off with 5 coins. And now what we're going to try and do is draw out this game as long as possible. So how do we do it? Remember that we could get to a fixed point within 3 moves, but we want to do better than that. We want to draw out the game longer. So let's have a go. We can move this coin to here. Then we can move this, that's 1 move, that's another move. Then we can do this move here, that's also legal. So that's 1, 2, 3 moves, and then that's 4. So you see that if we want to, we can make this game last 4 moves. Okay? So in this case here, where we have 5 coins and 3 piles, the longest amount of time this game can go on for is 4 moves. Okay? So this is actually a much more interesting problem, is what's the maximum number of moves you can do in a game like this? And so my next problem for you is, what happens if you have 10 coins and 3 piles? So say you have 10 coins all starting in the first pile. What's the maximum number of moves that you can make this game go on for? Okay, and so now the open problem, the unsolved problem, is what happens in general. If you have a general number of coins and a general number of piles, what's the maximum number of moves that you can do? Now, this is a problem I encountered in my own research. I couldn't solve it. Some other professors that I talked with couldn't solve it. I don't know if maybe some Russian guy got the exact answer, but as far as I'm concerned, this is an open problem. And I have an approximate answer, but no exact answer. And I think it's possible to get an exact answer. So I think this is a very, very interesting problem. It's deceptively simple when you pose it with these coins. I mean, a nice way to actually look at the problem is to make some kind of charts like this. You see, this shows all the different moves that you can do when you have 5 coins and 3 piles. And you can see that we always end up at one of these 3 fixed points here. And so more generally, you're talking about these kind of lattices in high dimensional spaces, and it's very, very interesting. But the basic problem of what's the maximum number of moves you can do with a certain number of piles and coins, it's totally open. So have fun with that.